Okay, let's go ahead and get started today. We're going to do, this shouldn't take too long, but we're going to do something else that uses trigonometry functions. And in this case, we're going to apply forces using vectors. And to apply forces, it's really the same stuff we've done before. It's just a little bit different use of it. And so hopefully you're getting used to sine and cosine and using those to move things. Today we're going to use them to apply a force to an object that's in motion. All right, so let's go and get started. So the first idea here is let's review again. Radians, mathematically natural way to measure angles. We have a radius of 1 for a circle. Here's a circle, radius of 1. And the idea is how far around we walked, what angle does that put us at? So if this is over here 0, we start walking around to that. That'd be 90 degrees from where we started if we were to measure that. So at 90 degrees, that would be pi over 2. As we keep walking around, we get to pi. Then we get to 3 pi over 2. And then we get to 2 pi, which is the same as back to 0 again. So it's this mathematically natural way of measuring angles that is independent of the size of the circle, because pi is always the same. And if we say, well, that's a radius of 1, then it's 2 pi units to get all the way around to where we started. Pi units to get halfway around, pi over 2 units to get a quarter of the way around, and so forth. So the idea there is there are units of radians relative to their degree equivalents, but again, since radians are a more mathematically natural way where degrees are arbitrary, we use radians in the math libraries, the math module for Python. Okay, and then sine and cosine. As we walk around that circle, we're either somewhere above the line or somewhere to the left or right of the line. And this idiot's trying to mess with stuff. So we are either somewhere to the left of the line or somewhere above or below the line. I think he was on the microphone there. But the idea is that if we measure how far to the left or right, or how far up or down we are, that's what sine and cosine give. So again, we have a radius of 1, and so sine starts out being how far above and below we are. So as we walk, sine from that 0 degree point, or 0 radians point up to pi over 2, then that sine will go to 1, it'll go back down, and then when we go all the way back to 2 pi, where we've walked 2 pi units around, we're back to 0 again. You can see that here. It goes up, it goes down back to 0. We're on the line again over here. We keep walking. We're as far away as we're going to be on the negative direction. We're down here. And as we walk back up, we're back up there again. And cosine is the same thing, but rather than up and down, it's left and right. So sine up and down, cosine left and right. And I've reviewed this for every lecture for the past 3 or 4 for a reason, that this is important stuff to get really familiar with, so you don't have to think about it. And you'll note that in this case, the way we're thinking about it here, we don't have to memorize like SOHCAHTOA or same old horse came, whatever. I don't know what the other ones are. But as long as you remember that sine is up and down, cosine is left and right, and you know how radians work, and you know you're just walking around the circle and saying how far above or below, or how far to the left or right we are, you can reconstruct all of that. Okay, so here's the idea for what we're going to do today. We want to apply a force, which is just another application of the trigonometry we already know. So in other words, we have this spaceship. We want it so that it thrusts, produces a thrust force, which is going to thrust it in the direction toward the nose. And so we're just basically, while the thruster is on, we're applying a force to it. We're applying a force in the direction that the ship is facing. So to do that, we need to be able to add that force and have the result change the speed and direction of that ship. So in other words, if the ship is sitting still and then we apply a force, it should start moving. And the same thing is true in the world. So here's something, I apply a force to it, it makes it move. It doesn't move on its own. In fact, if I let go, there's a force causing that. It's gravity pulling it down. It's a force due to gravitation. So we need a way to apply that force, which is going to change the speed and direction of something. All right, now to rewind a little bit, if we go back to like Newton's first law of motion, it basically says an object will remain at rest or in uniform motion in a straight line unless it's acted upon by some force. So in other words, another way to think about that is if there is no force, so without a force, an object will move in a uniform speed and direction. It'll keep moving how it's moving. If we add a force, no matter what that force is, the object is going to have to change its speed and direction. So in other words, if we have something that's sitting completely still, like this, it's going to stay still unless something comes along and a force gets applied and acts on it. That force could be gravity. The force could be somebody hitting it to apply a force. There could be a lot of things that cause a force to be applied. But they're all kind of the same. It's just gravity's going down, my hand hitting it is going up, something could come in from the side. It's really just the accumulation of all those forces that cause the thing to have that change in speed and direction. Okay, so back to Newton's law. Here's our ship. Let's say there's no force acting on it. It's just moving, so ignore the thruster right now. It's just moving how it's moving without the thruster. Flying through space. Something is going to act on it later, but right now it's just moving. So right now, if it's at ship x and y, we would calculate the dx and the dy using sine or cosine and sine respectively. And then we know the next position it's going to be is ship x plus dx, ship y plus dy. And dy might have a negative value to move it up in this case. But notice that we're just adding dx to get the x over that position, adding dy to get the dy up to that position. And then the next point in time, if there's no force acting on it, it's just going to be dx again and dy again. We're going to have the same dx and the same dy. We just move that triangle up there. So this is ship x plus 2 times dx, ship y plus 2 times dy. In other words, we just take what we already had here and we add another dx to it. We take what we had here, we add another dy to it. And you can kind of see that here. Dx, ship x plus dx plus another dx, ship y plus dy plus another dy. Now, that will just continue moving in that straight line. But what if we have a force that's acting on it as it's trying to move in that straight line? In this case, like gravity. So we have this gravitational force vector here pulling it down, and we want to know where is it? Because it can't be where it was over here without a force, because there's something pulling it down that's going to make it a little bit lower than it would have been. So how do we compute that? Well, we basically just apply that force vector to the motion vector of the object. In other words, what we're going to do is apply the force vector to the motion vector, and that's going to give us this new x and y, which is going to be different than the one that we would have had before, because the force vector is pulling it downwards a little bit. Now, to rewind a little bit and look at how that works, the idea here is pretty straightforward. That the here, let's go back to here. So essentially, whatever the new x and new y would have been, with which we already calculated back here, it's just ship x plus dx, ship x plus dy. It's really kind of that same thing, but we're now also adding the dx for the gravity and the dy for the gravity. Since gravity straight down, the dx is going to be 0, so the x is in the same place, but notice the y is now going to be somewhere different. So in other words, this is going to be the new x plus the force x, the new y plus the force y. And we would calculate those based on how much gravity there is. Now, that's how motion or a force can affect that. And let's look at it in the case of over time. So here's the ship trying to move in a straight line, but with gravity applying on it, notice there's the first one, it moves it down a little bit. Here's that vector, which would have been a straight line from there. And here's gravity moving it down a little bit. And here's where the straight line would have been from there, gravity moving it down, straight line from there, gravity moving it down. And so notice that over time, as this thing's trying to fly sideways, it's going to have this kind of curved trajectory. And also notice it's going to start getting faster as it gets down here because it's accelerating. So that's no different than me taking this object and kind of throwing it sideways. And I know the camera shutter speed isn't great, but you'll notice that it flies in a kind of curved pattern. Maybe if I go a little bit slower. So if you notice that curve pattern, that's just the force of gravity acting on the object and being applied over time, just like we see here. So we could apply other forces that same way. The force of gravity isn't unique. It's just a force acting on that object. Same way as thrust would be a force, or friction would be a force, or drag, or an explosion pushing something away, or a black hole sucking something in. It's the same concept, just forces acting on things. So let's look at thrust particularly. So adding a thrust force. So let's say the ship is moving this way along this gray area, but it's facing slightly downward and they apply the thruster. So that's going to apply a thrust in kind of that downward direction like that. And when that gets applied in that downward direction, notice what we do is rather than this air going straight down like it did with gravity, it's going in the direction the force is being applied. So if we think about that, we've got two dx's and dy's. We've got the one of the motion vector, the one we would have calculated before, so we use cosine to calculate the dx, sine to calculate the dy based on the ship's speed and its direction of travel. And then you'll notice we have this force vector that we had here earlier, and it has its own dx and its own dy, which we're going to call f dx and f dy. And since the force, that's going to be in the direction the force is being applied for the thrust force, which is the direction that the ship is facing. So the ship is moving in one direction, that's having a force applied in the direction it's facing or heading in the other direction. So to do that, to figure out what the resultant is going to be, we just add the components of the two vectors. In other words, the resultant is going to be, the resultant dx is this dx plus that dx, which gets us to this point, and the dy is going to be this dy plus that dy, and this one happens to be negative here, positive, and that one's negative. So it's going to end up there. So one way to look at that resultant vector is it's really just this line that if we take the components of this vector and the components of that vector, and we just add the x's, the dx's, add the dy's, that gets us this new thing which has its own dx and its own dy, which those are easy to compute. Resultant dx is the dx plus f dx. Resultant dy is dy plus force dy. So we took this triangle, added this one onto the end of it, and now we end up there, which makes this new triangle here. Now that new resultant vector, we can then convert that back into a new direction and angle. And we know how to do that. We can get this, I should say new speed and angle. Let me fix that real quick. Direction and angle, the same thing. Speed. All right, so essentially what we have is an overview that looks like this. The overview for adding a force is step one, compute the motion vector components for dx and dy. And we know how to do that. That's just going to be using cosine and sine. And you'll notice that I left off the math dot here to make this a little cleaner. And I left off the conversion of this to radians to make this a little cleaner. And I also left off the -1 on the dy here. We'd probably want to add those in. But anyway, we're computing the dx and dy of the motion vector. How is the thing moving right now? And then we compute the components, the vector components, f dx and f dy for the force vector. And the force vector is whatever the magnitude of the force is. And then we use sine and cosine again. So it's the same math we did up here. We're just saying, what are the two components? What's the x and what's the y of that vector? That's this magnitude. And now that we've computed those, we can now compute the resultant by just adding those together. Add the dx and dy, or x to dx, f dx to dx, f dy to dy, and now we have the resultant vector. And now that is now how the ship is moving at a different speed and at a different angle. And so now we just compute those. So ship speed, we do that with Pythagorean theorem. Square root of the r dx squared plus r dy squared. We're just solving for the hypotenuse of that new triangle down here. We're solving for the length of this. And then the last thing here is computing the angle. So that's computing the angle here. And we do that using arctangent 2. And this one I did put math.degrees and math.a10 too. But r dy, r dx, and this is negative because the thing is negative. These should be negative. We'll fix that when we actually write the code. But now we should have something that we can apply a force to. So let's go to the code and let's write it. So we're going to start with our code from last class, but we're going to add a thrust force and allow the ship to now move. Before it was kind of pinned in the center of the screen and we had like a thruster showing up out of the back, but we really weren't applying any force and having the thing actually move anywhere. So we're going to need to have two angles though associated with the ship. One is the angle that it's traveling, and one is going to be the angle that it's facing, or the way that it's pointing. And so we're going to add another variable for that. And let's go ahead and switch to it. Let's get right to it. So let me switch over to the code. Okay, so here's the code from last time. And if you look at that code from last time, you'll notice that this draw ship is just the code for drawing it. This is exactly what we had last time. One exception, I did add int, the int function call around these, because the new version of Pygame wants those things to be integer, and it complains at you if you pass in floating point values. And since these are coming from sine and cosine that are calculated up here, we could have done int around all of these up here, I suppose, rather than doing it down here. But I just went ahead and put them down there. Now, let's remind ourselves what this code actually does. Okay, so here's the code from before. We can rotate the ship. We can apply the thruster at any angle. But when I thrust, and I'm using spacebar, I'm going to switch that to W here, I think, in a second. But you'll notice it does not move the ship. The ship is stuck in the middle of the screen. So the first thing I'm going to want to do is have the ability to have that thrust apply that force. All right, let's go back to the code. All right, we already have this thing that's ship thrusting if it's true or false. So what I'm going to do in here, and let's make sure the ship has a speed. Yep, so the ship has a speed and it has an angle, but we're going to need two angles. We're going to have the angle that it's facing, and then I'm also going to make a variable that ship angle travel. And I'm going to actually start them both at 0. So travel is how it's moving, facing is the direction it's pointing. So that way, for example, you could point the ship, in a direction like this, and the angle it's facing is that, but it could be traveling this way, but then it could rotate it like that. So it could keep traveling in a way and rotate as it's traveling, because that's, imagine like a car skidding on ice. The direction it's facing might be different than the direction that it's moving. So there's one of these is moving, one of them is the way it's pointing. Okay, so let's add the code to actually move the ship. So here, move the ship. And to move the ship, what we're going to do inside of this code is I'm just going to compute the dx and dy. So dx equal, and if you remember how to do that, that's going to be the ship x, or for the dx, it's going to be the speed, so ship speed plus, times math dot. Now this is x, so this is left and right. So should x be sine or cosine? Should be cosine. Math dot radians of ship. Now this is how it's moving. So this is not the angle that it's facing. This is the angle that it's moving. So let's go back and look at that variable. So that's the ship angle travel. And we could actually make this, here, let's just make this facing and moving. Ship angle moving. All right, so that's going to compute the one component of our motion vector. Now let's compute the dy. dy equal ship speed times math dot. Now this is dy, this is up and down, so sine is up and down. So sine math dot radians ship angle moving. So now we have the ship dx and dy. But before we actually do anything with that, we're also going to compute the, here, let's change this. Let's call this compute. Having some typing difficulty. All right, so we compute the motion vector displacements. Now let's compute the force vector components. Let's go ahead and change this from displacement to components to make these match. Now this, we're going to call FDX, and that's going to be the force amount. So in this case, I'm just going to set that up here. So let's say, actually, I'm going to set it inside of here. So if the ship thrusting is true, and the ship thrust amount equal, let's make this really small for right now. So that's if they're thrusting. If they're not thrusting, we will set it to 0. So in other words, when they press the thruster, it says thrusting is true. That sets the ship thrust amount to 0.1. So down here, we're going to take the thrust amount. So ship thrust amount times, this is going to be the same math we had before, so math.cosine, because this is x, of math.radians of, and in this case we don't want the angle it's moving, we want the angle it's facing. So this is going to be ship angle facing. And now we're going to do the same thing for dy. Let me fix my awful typing here. Except this is going to be sine. Now there is one other thing that we need to do, and that is remember that the y-axis is inverted. So let's go ahead and just multiply each of the y components by -1. We'll do it here and here. And that's the only reason for that is because the screen is kind of upside down from the normal Cartesian coordinate system. Okay, so now we have those. Now let's compute the resultant. So the r dx is going to be dx plus f dx. R dy is going to be dy plus f dy. And now let's go ahead and apply those. Apply we're going to apply those to the ship. And essentially what that means is we're going to say ship x plus equal resultant dx, ship y plus equal resultant dy. Now there's one last thing we need to do, and that's we need to convert back. And that's, we need a new ship speed and angle. So here, to convert those back, we said we're just going to use Pythagorean theorem for the speed. So ship speed equal, and we just need to use the resultant dx and dy. So here, r dx squared plus r dy squared, that whole thing, square root. And now the ship angle. Now this is going to be the angle of travel, so the angle moving is going to be equal to math.degrees, math.atan2 minus r dy, r dx. And again, the minus there is to undo the inversion that we did with these two up here, because the screen's positive going down and negative going up. Okay, so now we have a new angle and speed for that. Now, because we moved the ship here, there's one other thing we should do. We should probably wrap this thing around so it doesn't leave the screen. Otherwise, it'll just go off and it'll be gone. So let's add that. So if ship X is ever less than 0, then ship X equal 799. If ship X ever gets to be greater than 799, then ship X equals 0. So that'll wrap it on the left and right. And let me add a comment for this. Now let's do the same thing for Y. So if Y is ever less than 0, then set Y equal to 599. If Y is ever greater than 599, then set Y equal to 0. All right, let's run this and see what happens. And we have a problem. Okay, ship angle, we need to change that down here. So when we go to draw it, this needs to be the angle that it's facing. Let's try that. Okay, so there's our ship. It's, all right. That's in our if statement up here, because we changed this from ship angle facing. And I also said I was going to change this from a space to be a W. I think that makes more sense to push forward to thrust. All right, let's see what happens. All right, so we can rotate. And notice we are applying that force. And if I keep applying a force in a direction, all right, we had it leave the screen. Let's figure out why. We screwed something up somewhere with it leaving the screen. Oh, typo. There we go. All right. So there it is wrapping. If I want to stop it, I need to apply the same amount of force in the opposite direction. And that force might be a little bit high right now. Let's make it a little bit slower so it's a little more sluggish to control. So let's lower the force a little bit. All right, so now it takes a little bit of effort to bring it up to speed. And if I want to stop it, I have to point it in the opposite direction. All right, let me rerun that again. And notice this now kind of matches, like, okay, let's say this is a rocket on the launch pad. And when it goes to take off, 3, 2, 1, you'll notice that as it goes, it kind of picks up speed and picks up speed and picks up speed and goes faster and faster and faster. And if we start changing the angle from there, we could actually reach escape velocity and then get into an orbit around the Earth like that if we had a bigger screen, obviously. But you'll notice that this is accurately just applying that thrust force in the direction that the thing is facing. And you could apply other forces like this as well. So for example, we could apply some sort of gravitation that's always in the downward direction. We could make it so that Y actually bounces off the walls. So it would bounce, have that downward gravity force always being applied. We could also add friction that kind of slows things down. So when we're moving like that, it would eventually slow down to stop. But you'll notice that now that we have a way to apply any arbitrary force of any magnitude in any direction, looking at the code, we could apply that in here we computed the force vector, here we applied them. To apply other forces, we would just compute the components of that and add them to this. We could just accumulate all of those forces that are being applied to something, and build that up and build that up and build that up. And that can be a really powerful thing to understand, because every force that's applied to something is going to work in that same way. So you want explosions in your game that blow things away. You want wind that knocks things over, affects things. You're making a game and there's grass, and the wind needs to blow and the grass needs to blow in the breeze. You can do that. All forces are really just applied in that same way. We're just taking that force, computing the component of it, applying it to the way the thing is currently moving, and then that could be true for gravity, or an explosion, or a vacuum cleaner, or a helium balloon that's trying to float, or a buoyant force in the water. All of those are just really a vector pointing in some direction that's acting on that thing. And in fact, you could have forces that act on different parts of an object in different ways. And as a quick inspiration for that, let's go back to the slides for just a second here, and then I want to show you something just for fun. All right, so we added that to our code, and that's all we're going to do. Next class, we're going to look at how do we do with multiple objects, and we're with a thing called sequences. And we've been using sequences or lists. We just haven't really known that and haven't really talked about them. And we're also going to start talking about a concept called object-oriented programming that's going to make a lot of this a whole lot easier. So we're going to start off with some basic stuff with sequences, specifically with lists. We've been using lists with like colors like red, green, blue, or the list of points in our, here, let me switch back to this and show you where there's a list. Up here, this is a list of points, point 1, point 2, point 3, and these things are a sequence called a tuple. It has a pair of things. So this is a list of pairs, and so we're going to, and here's a list of the color component values called a tuple. It's not a list, it's actually a tuple, but they're closely related. But you'll notice that we've been using those, we just haven't really talked directly about them. Now the thing I want to show you though, quickly before I turn you loose today, is we talked about like simulating those forces and things like that. So here's a technique, this is actually from a presentation that I did at the Shawnee Gaming Conference years ago. And let me go and show you. This is all just Python. It's really not even that much code here. It's just, and notice it's doing the same kinds of things that we do in here with sine and cosine and things like that. Notice here's some of the math in here. There's computing the length. There's the stuff in here with computing. Actually, I have some of that in there using sine and cosine. But let's run this and see what it does. So this is actually a program that is written in Pygame, just like the stuff you're doing. But this is applying forces between each of these little nodes. So each of these circles has a, here, and I made this so I could grab a hold of parts of that. But you'll notice that this is just applying a force between each of those things, trying to keep them a certain distance apart. So if I stretch this, it's kind of like a rubber band. And if I let go of it, it springs around like a rubber band. I can actually also cut some of those little connections between them and divide that in two. Cut that one too. Cut it off again. And I also have the ability to then connect those into like a grid shape rather than being just a and so now I have this kind of rigid body and I can drop it, and you'll notice it'll kind of, I can take it and like throw it against the wall. I can actually get it to deform. Here, let's look at, there's a box created of these. So I can grab that. I can kind of get it spinning and then throw it. But you'll notice that this is the same kind of math we're using on the other stuff. But we have this kind of physics simulation that happens because of that. And it's the same kind of thing, applying forces to these things. In other words, when I stretch those lines out, they have a certain length they want to be. So they kind of have a force toward each other if we stretch it. If we push them together, they have a force that pulls them back out. So here's an example. Let me turn on this ball tool. So with this actually is exerting a force on that thing. And notice I can get it like kind of like a bar of soap. I can kind of squish it in the corner here and then get it to spring out of there. And that's just applying those forces to those points between themselves that are trying to maintain that position. Those are called stick constraints. And if I really smash it, I can make like this thing that's now collapsed down into like a small thing. I can kind of push it against the wall and get to spring out of there. All right, let me make a couple other shapes here. So that's that. There's like a thing. It's kind of a star shape. And then move the ball out of the way. You notice I can grab that. I can actually grab it. Let me grab that and then pin it here. And then I can take the ball and I can move it up. But this kind of physics simulation is the kind of thing that you have in like right now the yellow ones are pinned, so I can unpin that one and it'll hang from one. Here, let's pin it from a different place. Let's pin it from there. And let's unpin this one. And you'll notice it'll like naturally move sideways, and now if I take that ball and move it, I can kind of rest this thing on the top of the ball. Okay, let me pin that. Now let me move the ball out of the way. Now we can kind of boing. All right, that looks a little questionable. Maybe we shouldn't do that one. But anyway, you'll notice that this is how you have physics stuff in games where stuff moves. And really, the only math that's in here is just applying forces when the sticks are longer than they need to be, or applying a force in the other direction when they're shorter than they need to be. And that's it. And that gives us the ability to do this stuff. I also have the ability here, I can cut this. Let's switch to the cut tool. Let's cut part of this off. So let's say, what happens if I cut this constraint here? There's a lot of force on that one. So let's say that one breaks. And now you'll notice the thing is free to swing around. I can actually cut that whole thing off. I can cut some of these things. Grab that. All right, let me look at a few more of these. Here's a cloth that's made out of these. So if I take that ball and I move it up there, the cloth will kind of drape across it. So if you've ever played a game, I don't know, let's say Assassin's Creed, and there's a cloak blowing in the wind behind the player, or you've played like, I don't know, like the Hitman games, and you walk through a cloth and push it out of the way, and it kind of drapes across the body of the player as they walk through, and then it kind of blows in the wind. You can kind of see this here. This is all Pygame, stuff that you could do with the same math we've already done. It's very simple. So the math that we're doing in here with the sine, the cosine, here we can, here let's unpin some of these. And let me grab that ball again and move it up under here. The cool thing about this stuff is, and then I have a deteriorate too, which will kind of make the cloth kind of fall apart. Now the ball's kind of stuck in the middle of it, kind of behind it. But this kind of stuff, that if you learn how sine, cosine work, how tangent or arctangent 2 works, how radians work, this stuff is not that complicated. Again, the code for this, every bit of that code for this is right here. So notice that there's we'll get into these objects. We haven't talked about those. There's a class for a point, a class for a stick that connects it to, a point group that's like the collection of things. And then I've got some functions that check to see if a circle have collided with another circle or a line. Down here I have this make star thing, make rope. These are the things that actually create those original shapes. That's the most part of the code here. Make cloth, make blob. We didn't look at the blobs yet. We'll look at this in a second. But the actual code to actually move the stuff around and make it do that is really just this stuff like right here. This is it. It's very simple, which makes it very fast. And it's really just applying kind of those trig kind of functions. Let's go back to that program and look at the last couple here. Let me move that ball out of there. And let's do, there's the cloth. Here's another kind of cloth where these are cross-linked, so it's a little more sturdy. It's a little bit stiffer, more like a, instead of like a really thin cloth, this is something that's a little more like a sheet of paper. And I can actually unpin that guy up there. Or here, let me repin that. Let's pin this here, right there. I'll pin those two, and then I'll unpin this guy. And the cool thing about something like this is this can also be used to do like non-inelastic collisions where something gets smashed and deformed. So watch what happens if I smash this ball into this really hard. I've now kind of dented it, and it's kind of locked it into like these other positions where I've smashed the thing up. All right, let's redo that and make it deteriorate now. And what deteriorate does, it just picks some random lines in there and then it makes them fall apart. So you can kind of deteriorate the whole thing eventually. All right, let me get that ball out of the way again. Or here, I can put this here and make it fall in the ball by, here, let's do a cut. Let's cut all of these guys. Let's cut that. And then let's cut those. Now we have this thing kind of balancing on there. It's also constrained by the sides, but it should eventually like kind of squish to one side there. And now there's so much force in the middle, it's kind of folding in on itself. So now I've taken our paper and I've crumpled it up into a ball. Now let me grab it. Maybe I can spin it back out again. All right, but anyway, oops, let me run that one more time and look at the last couple shapes in that, just for fun. All right, so there's that. We had that one. This one is a like a piece of paper, but these constraints are less powerful, meaning there's less force between them. So now it's more like a more rigid cloth rather than something that's more like a solid like that. And then the last one, this is kind of a blob shape one. So if you ever played a game that had like blob shapes in it, notice that I can get the blob rolling. It'll kind of bounce off the wall, kind of squish this down, push it over there. I can get the grab tool and just grab that guy and toss it up in the air. And then there's one final blob here that's like a ring blob, which is much less stable, more squishy. But again, with that one, let me get the ball and I'll nudge that thing. But this is all the same math, the same kinds of stuff you're learning. There is a special technique for doing the physics simulation in this, which is what the topic of my talk was. But really, you could do all this with the stuff that we've already done in this class. The technique that I'm using in this is just, it's called Verlay Integration. And it is basically just a way to do the same kind of calculations that we're already doing a little bit faster. And if I cut this, let me do a... I don't know what to call this shape, but it's kind of like a flapping bird. Okay, so that's enough of playing with that for now. But just as a little bit of inspiration, that the stuff we're learning in here has, while it seems simple to apply this thrust force and have this thing move, and we're using sine and cosine for moving it and sine and cosine for the force and adding them together and using the arctangent 2 to calculate backwards and Pythagorean theorem to get speed, all of that stuff has really powerful uses, not just for the little things that we're doing in this class right now, but it has really powerful uses for the like AAA title kind of things that you're going to want to do eventually in your career. All right, so that's all for today. Make sure to work on that lab, the kind of balloon massacre lab. See if you can get that one done and working, because next class we're going to start adding multiple game objects all moving at the same time and be able to create objects to help organize our code to make that really easy. So in other words, we're going to want to have in the next week or so bullets flying all over the place, doing all kinds of things with multiple enemies and the bullets hitting the enemies and asteroids falling and being shot by the bullets. So we're going to add all that stuff here in the next couple classes. Now, one question that has come up that I've had in email that I want to answer before I'm done today, and that is, what are we doing about the final? Because this semester is kind of a little bit messed up because of the COVID numbers dramatically increasing. And so essentially what the university decided is when you guys go home for Thanksgiving break, you don't come back to on-campus classes. And that's made it difficult to do a paper final exam, obviously, because if you're not around, I can't have you sit down with the paper and have a final exam. So what we're going to do in this this semester is I'm going to give the paper portion of the final exam on the last regularly scheduled day of class. And let me switch to where you can see, hopefully, the calendar. You can't quite see that. Hold on a second. Okay, so now you can see that calendar there, mostly. Let me move this over just a little bit more. There we go. Right there. Okay. So now looking at the calendar, today is Monday the 9th, and the last regularly scheduled day of class for you guys is the 23rd. So on the 20th, because this is Thanksgiving, it's happening here, and your move out time is the 24th. You have to be moved out by then. So we're going to have our paper portion of our final exam on the 23rd. And so you're going to take that paper portion of the final exam on the 23rd. And then that next week here during the normal finals week, which is the 7th as the normal finals week, I'm going to post the programming part of the final exam. And it will be kind of like a lab that you'll have time to work on that. You'll read what it requires you to do. You write the code. You submit the code like you've submitted your labs. And then that will be it. Now, we do have some other topics I want to get through with the remaining class time we have. So in other words, today's lecture is the 9th. The next one is the 11th. The 11th, I want to get through some object-oriented stuff and some sequences. And then we're going to do some more stuff with objects. We're going to do lists of objects and do that. And there's going to be one more lab that you'll have that's posted. And then that will take us up through here. And then on the 18th, I'm going to post the study guide. And we'll have time to work on the lab and do that. And then you'll take your test here. After Thanksgiving break, we've got 2 more classes where I'm going to do a couple more lecture things that I want to get in before the end of the semester. And then we have our finals week here, December 7th, in this area here. So that will take us up through the end of the semester. So just be ready for that study guide. Be ready to cover a few more topics. Let me go back to this, and let me switch this off. And actually, let me go to the end. So, let me go to the end of this. All right, so that's where we finished up. Next class, multiple game objects with sequences. We'll start with sequences. We're going to add some object-oriented programming that's simple to start with. We're going to write some sample code. And if it would help you and you want me to post the sample code that we've done on the course page, just let me know, and I can certainly do that. I hesitate to do that because I really want you to watch the lectures too and not just look at the code and copy and paste what I'm doing. I want you to understand it. But if it'll help you, at some point, let me know, and I'll see what I can do. So that's it for today. Everybody stay safe, work on your labs, and be prepared for that final exam on that Monday before you leave campus. And be prepared for another lab coming up in the next couple of classes. And that's it. Stay safe.